Ciao! Here is a conversation with Elisabet Canalias. Dr. Canalias is a mathematician and aerospace engineer working in the flight dynamics department of CNES, the French space agency. Her focus is in interplanetary trajectory design, and she's mostly known for her participation in the landing operations of the Philae probe on Comet 67P Churyumov-Gerasimenko. Her more recent endeavors, again focused on the exploration of minor bodies, include the Martian Moons exploration mission and the trajectory design in strongly perturbed environments for the study of Phobos and Deimos, and the Hayabusa 2 mission, again in collaboration with the Japanese Aerospace Exploration Agency, particularly focused on the dynamics and operations of the MASCOT lander. I hope you enjoy it. To support this project, please subscribe to my YouTube channel, connect with me on Twitter and LinkedIn, and support me on Patreon with a monthly membership, following the links in the description. I could read about your work about the Lysage's orbit. Can you describe maybe a bit your work of your PhD?
So after my mathematics studies, I had the chance to be accepted or to be integrated in a research group in Barcelona, with a lot of people involved in dynamical systems theory and applications to mission design and to Lagrange points mission design in particular. So I just took advantage of this to pursue a research topic which is very applied, but with a strong mathematical background. As I said, relying on dynamical systems theory for applications in the computation of orbits around the Lagrange points, L1 and L2 mainly. As you said, Lysage's, Lyapunov, all the classical orbits around these points, their manifolds, and the applications of these manifolds to see what can be done to solve some of the mission analysis problems, such as station keeping, the transfer from Earth, transfers between different orbits. So this was more or less my PhD was mainly, I was lucky because I found the people that were very good on this, who were able to give me some advice. They had a lot of publications in which I could, which were a good starting point, and then I found that I was passionate. I loved that topic, so that's more or less in a few words, the research I did during my PhD.
Yeah, if I can add something to that, coming a lot after that, I still could read the book Dynamics and Mission Design Near Liberation Points, which I guess is from the group you joined during your PhD, which is, I mean, for me, it was really a moment in which I said, okay, I want to do this. I like this. This is what I would like to do for.
Yeah, and my contribution to this is just a tiny thing compared to these books and the publications of the group. So
the books were
as
older.
I said, yeah.
Okay.
A little bit, yeah. So 5-10 years older.
Okay. And then, can you describe what you did after your PhD?
Yeah, after my PhD, well, actually, during my PhD, I got a call, or rather, I should say, my advisor got a call from ESOC, from the European Space Agency, because they had a very particular topic they wanted to develop, and they were asking if we could establish some kind of collaboration with PhD students or recent doctors. So I was contacted. Well, my PhD advisor said whether I was interested in that, and I went to Germany, to Darmstadt, to ESOC for 4 months with another student, PhD student of the group. The topic was related to libration orbit design and station keeping for the Earth-Moon problem around L1. And it was there during this 4 months, this kind of internship at ESOC, that I really saw the light, or I said, this is where I like not only from a theoretical point of view, but I want to work in an environment like this, designing real missions or preliminary studies for missions that may become real in an international environment. So that was the starting point, let's say, of my post-doc or postdoctoral period. Because then I went back to Barcelona, I finished my PhD, but I knew I wanted to apply for a postdoc at ESA, in particular ESOC, because it's where the mission analysis, a lot of mission analysis activities are performed. So that's what I did. After my PhD, I went to ESOC for 2 years as a postdoc, and I stayed for 1 more year as a contractor. During my time there, I did the postdoc was in the mission analysis section, working mainly for what's now JUICE, the mission to Jupiter, but only as a support to the main designer. And then also a little bit on Herschel Planck, which was launched just after my postdoc. And during the year I spent as a contractor, I was in the flight dynamics department for interplanetary missions, but really touching to a little bit more to operations for Rosetta, Mars Express, and Venus Express. So that leads, so it's PhD, 3 years at ESOC, and after that I got my position, my current position in Toulouse, in the French Space Agency, in which I've been doing a little bit of everything, but yeah, always related to celestial mechanics and flight dynamics, mainly for interplanetary missions, a lot of preliminary phase 0 studies, some operations for instance, the early orbit operations for some of the Galileo launches. But this was not my field of expertise, but I got the chance to do this. And also missions to small bodies. So I had the chance to be in the team for Philae lander from Rosetta, MASCOT for Hayabusa 2, and currently working in some mission design topics for the Japanese mission to the Martian Moons, MMX.
Okay, could you maybe go in detail about these missions to minor bodies? I mean, there have been quite a lot recently. Hayabusa 1, Rosetta, you mentioned Hayabusa 2, recently recovering, coming back to Earth, let's say. OSIRIS-REx recently touching down to Ryugu. So could you mention maybe the similarities between these missions you worked in and the differences?
It's not easy. Well, as you said, they are all.
I mean, always from a mission design point of view, huh?
Yeah. In other, it's anyway, it's the field of my, let's say, field of expertise, if I have any, and I cannot talk about science or anything else. But as you said, they are all missions to small bodies. So missions to bodies which are outside from the Earth environment, but not other planets. So asteroids, comets, and for MMX, it's planetary moons. This is a topic which in the last decades, let's say, has raised a lot of interest because the scientists believe that this may lead us to better understand the formation of the solar system, ultimately, I guess all space exploration, or most of the space exploration, leads to why is there life on Earth, and how did this develop. But as I said, science is not my field. So from mission design point of view, let's say the work we did for the mission Rosetta was restricted. I'm talking about CNES to the lander that was on board of this mission, called Philae, which was a German-French lander. So what we were in charge of computing or designing the best separation parameters from the mother spacecraft and the descent trajectory to ensure a safe landing and the possibility for the lander to do science afterwards. So mainly for flight dynamics, this was the role of CNES. We were, of course, our interfaces were at ESOC, who was fully responsible for Rosetta mission, and we did not do anything on Rosetta trajectory. And also on the other side, we had the German colleagues who were responsible for, let's say, the platform, the Philae itself, the instruments and the platform. So the operations done at CNES were flight dynamics and science planning. So the I think it was a 10 or 11 payloads on board of Philae. Somebody had to organize and decide when each one of them was doing science. So this was done at CNES as well. Flight dynamics and mission, scientific mission planning for Philae payloads. But the rest was done in Germany, and for Rosetta, everything was done in the European Space Agency. So this kind of structure repeated a little bit for MASCOT. So then the next mission, chronologically, Rosetta, the landing of Philae was in 2014. And a couple of months later, Hayabusa 2 was launched from Japan. This is a Japanese mission. So the people responsible for the mission changed a little bit. We went from the European Space Agency to being partners of JAXA, the Japanese agency. But for the lander, it was again a Franco-German, German-French collaboration with more or less the same structure, flight dynamics at CNES. It was simpler. There were less payloads on board of MASCOT, and the mission was shorter. The mission on the asteroid. So the work we did was more or less the same. Considering all differences between the bodies we were targeting, because for Rosetta it was a comet, for Hayabusa 2 it was an asteroid. Philae had some engines. The separation was really far, 20 of the order of 20 kilometers from the comet. For MASCOT it was several meters, so several hundreds of meters. Now I don't remember the exact, but it was closer to the asteroid. MASCOT had no engines. No engines. It had to rely on its batteries for the mission. So for MASCOT there was no extended science phase planned, only the duration of the batteries. So apart from all these differences, the work from flight dynamics was to compute the best separation conditions and the descent trajectory to ensure the scientists could do as much science as possible, taking into account all the technical constraints. And so these two missions were kind of, it was good that they came one after the other. The teams, both at CNES and DLR, the German agency, were not exactly the same people, but a lot of people involved in one mission were also involved in the next. So we could take advantage of the experience and improve our tools, improve our knowledge, and I think that was good for both missions. And the last one, it's the current one, the one I am working on nowadays, is a little different from this one, because from these two previous ones, because it's going to a moon already. So the dynamical environment is quite different. The moon is close to the planet, so we have to take the planet Mars into account in all the computations. CNES is involved as a support mission analysis team with JAXA to the spacecraft, to the mother spacecraft mission design. So we can participate a little bit in saying which kind of trajectories the spacecraft will fly for the moon's exploration part of the mission. So once in Mars, for the Phobos, mainly for the Phobos proximity phase, we participate in that. And for Rosetta and Hayabusa 2, this was not the case. We were restricted to the lander. There's also on board of MMX, there's also a French-German, again, lander. So CNES and DLR are developing together. In fact, this time it's a rover that it's supposed to move on the surface of Phobos. Okay. There's a team at CNES dedicated to that. And yeah, and the third contribution of CNES to this MMX mission is in the science side. It's a French instrument that's been developed in the French department, in the French laboratory. and we coordinated from CNES.
Okay.
So this one is quite different in terms of the type of body the mission wants to explore and the type of work from a more personal point of view or a CNES point of view. The type of work we are doing from MMX is a little bit larger than the one we were doing for the previous missions in terms of flight dynamics.
And are you in contact with other people in JAXA working on trajectory design as well? Or is the part of trajectory design fully responsibility of CNES?
No, it's the responsibility is on JAXA side. So it's a Japanese mission. JAXA decides mainly which kind of trajectories or when they want to fly in which region. And we intervene, we just participate in validating or proposing, suggesting new scenarios. It's a support role for the mother spacecraft.
Okay, and about the work you do in trajectory design, how much of what you've done in your PhD and the previous missions come in handy? I mean, are there manifolds that can be leveraged in the MMX mission, or do you need some new methodology?
So for MMX, it's actually the one in which what I learned in my PhD is more useful, even if it's not exactly the same case. But as I said, the spacecraft is always in an environment in which there are the moons and the planet. So it's not like when you go explore an asteroid and there's only the tiny gravity of the asteroid and the perturbation by the sun. In this case, it's a three-body problem most of the time. There are other bodies, but the main, when you are exploring Phobos, it's Mars, Phobos, and the spacecraft. So it's a three-body environment. The kind of trajectories we compute are not are not related to libration point orbits because due to the mass and distance ratios, these L1 and L2 are inside Phobos. The model, the real physics is quite far from the circular restricted three-body problem in which these objects are computed. So it's not really libration point mission design, but it's definitely three-body problem with perturbations. And we use different kinds of orbits, distant retrograde orbits, non-Keplerian orbits to observe Phobos in this complicated dynamical environment. So it is here that I came back to the dynamical systems theory, and not in a sophisticated or very theoretical point of view, but yeah, it's the kind of work I've done since I finished my PhD that resembles or that it's more related to these PhD works. For the other ones, the landing on a comet and the landing on an asteroid, as complicated as it can be, it's not complicated because of the n-body dynamics, but because of the, for instance, for the comet, the outgassing, and for both the comet and the asteroid, for the irregular and unknown surface and gravity properties of the bodies. So,
and this is not
yeah.
the case for MMX. I mean,
Also,
the gravity field.
it's also the case because the Phobos gravity field is known from previous missions, but one of the objectives of the mission is to refine it and to know it a little bit better. But okay, it's a moon. Mars has already been orbited several times by a lot of missions, so let's say we have more information than what we had from Churyumov or for the asteroids that the small body missions explore usually.
And why is it called Martian Moons exploration? I mean, why is it plural? You always mention Phobos. What's the whole plan of exploring both moons?
Okay, I always mention Phobos because the collaboration in celestial mechanics, flight dynamics, mission analysis started for the Phobos proximity involved mainly on the Phobos proximity phase. Then it's the name of the mission comes from JAXA because the idea is to explore Phobos and Deimos. But what I can say is just that we've been involved in the Phobos proximity phase, and this phase will probably be longer than the Deimos exploration phase. And I don't know if there are plans of getting in a kind of pseudo orbit around Deimos, as there are for Phobos. So for Deimos, they may only be flybys.
Okay. So
But
the
this
big
has to
part
be
of the
checked on the
mission.
official the official communications by JAXA. As I said, the responsibility of the whole mission planning or what they want to explore, it's mainly on JAXA side.
Okay, I see. And I don't know if you can answer this question, but what are the reasons of the collaboration between European and Japanese and the Japanese agency? I mean, are there historical reasons behind it, or are they recent? What are the reasons behind it?
Um, I don't. My opinion is just. I mean, my point of view is just from the technical engineer who had the chance to participate already in two collaborations between CNES and JAXA, and I say had the chance because I think JAXA is doing great things in the last 10 to 20 years in interplanetary mission design. So it's a chance to be able to be partners with someone who dares, with someone or an entity who
Uh-huh.
has the means and the courage to explore the things they are exploring. So for me, it's just a chance. I do not ask more. And I think it all started with science. They wanted to have on board some of the French instruments
Okay.
that are good in spectrometers, and it started as a scientific collaboration. They are kind of, from what I've seen, they are kind of open to international collaborations on JAXA, at JAXA. They also have usually American instruments in the mission, so they are not a difficult partner if the payload is good and justified. And then this scientific collaboration turned into a little bit more technical. There was some room, I guess, for a lander for MASCOT on Hayabusa 2. The French and the Germans suggested a good lander. The collaboration worked pretty well, so it has been more or less repeated for MMX, but I don't know the details. I do not take
Mhm.
any decision. So
Right.
from a political point of view, it's good. From a technical point of view, it's really good for us who want to work on interplanetary missions. And I hope it continues in the future.
Mhm. Right. And maybe we can talk a bit more about the collaboration with JAXA, going back to MASCOT, the work you've done for several years related to Hayabusa 2. What was the main challenge associated to that mission, to your part of to your workload associated to that mission?
Mm, the main challenge was, well, both for all these missions, it's never my work. It's always a team. So I'm just
Yeah,
a
sure.
tiny part of an extractor that is organized for these projects. But for MASCOT, the main challenge was that you were more or less throwing a dice, as the coordinator of our flight dynamics activity said. You throw a dice on a surface that you don't know, and you expect it will fall on the right side and it will be able to perform science. Uh, in addition to that, because there were no engines, no control, no attitude control, so it just goes down. It's stabilized a little bit during the descent, But then once on the ground, there's the bouncing.
Mm-hmm.
The bouncing that happened for Philae that was not supposed to happen for MASCOT was planned from the beginning. But knowing it will happen gives you no clue about how or for how long it will happen, even though we collaborated with very good people, very good research groups on these topics, on the dynamics on the surface of small bodies. But there's a lot of it that we still don't understand, and there's a lot of, let's say, random transfers of energy. The rocks, the boulders you find on the surface may deviate your trajectory one way or the other. If you fall on soft ground, you may get stuck. So the main challenge was the lack of control of what was going to happen.
Mm-hmm.
So all the studies were done in large zones. I mean, there's no deterministic trajectory for the bouncing. So
Okay.
you until MASCOT stopped, no one could say how long would it be bouncing and where it would stop, more or less.
Okay, but the design process was still deterministic, or you did some kind of stochastic optimal trajectory design?
There was a tiny part which was more or less deterministic, which is once you know the gravity pull of the asteroid, the separation conditions for the first touchdown point can more or less be computed in a deterministic way, of course with the dispersion analysis that go with the possible separation errors and the percentage of error we have on the modeling of the asteroid gravity and shape. So the first contact point was more or less could be predicted, but then the rest of it was stochastic, a lot of Monte Carlo simulations and choosing how to say, the most robust landing zone that would allow to do science in the highest percentage of the cases that lay in that landing zone. You never talk about landing points or stop points because it's impossible to predict. Even for the first contact point, you have a small ellipse due to the dispersion, due to the position and velocity errors of the mother spacecraft of the separation delta V. So even for that, you have a zone. But when you add the bouncing, you multiply this zone by,
Mm-hmm.
it's much bigger. So it's stochastic, yeah.
Okay, and when you talk about zone, you mean covariance analysis. You study the
Uh,
standard deviation associated to the
yeah,
state.
but yeah, covariance, but not theoretical. It was rather Monte Carlo
Okay,
dispersion analysis, performing a lot of runs and seeing what you get.
okay. And why was Hayabusa 2 successful and not Rosetta in this regard?
Ah, no, no, both were very successful.
No, I mean the bouncing. You said
Yeah, yeah.
that was not
The
expected.
thing is that for mascot, it was foreseen. It had no means to get attached to the ground, so it was bound to bounce. Um, and for Philae, the thing is that the separation and the landing were performed perfectly. Our ESA colleagues did a great job. The scenario that was chosen was very robust to even going down from more than 20 kilometers. It landed where it was supposed to land. The thing is that it did not get fixed on the ground as it should have. So
And this
the
was
bouncing
due to
was
the
not
low
predicted
gravity.
because of yeah, I don't know the details, but that was something that was supposed to be triggered once the first contact with the ground was detected.
Ah, okay.
Kind of harpoons to penetrate the surface and anchor Philae on the ground, and that did not happen.
Okay.
So
But
with
the
the
trajectory design
energy,
was perfect. Let's say
the trajectory design was good, and the performance of the separation was very good. The accuracy of the first landing point was as expected. The only problem was that it did not stay there, so it moved into another region with bad illumination conditions, so the long-term science was not possible for Philae. But again, this was just a part of Philae mission. Rosetta was very successful. Philae landing was successful. It was the first attempt to land on a comet, controlling more or less the trajectory, so it was successful. There was this mistake or this malfunctioning of one of the subsystems that prevented Philae from staying put in the place that was chosen. So, but both of them were successful. And MASCOT, the difference was that we were expecting some bouncing, so it was like this, and it was as expected.
Okay,